Good morning student, myself Melissa, and in today's session topics slope and deflection, we solve the example of Castiglione theorem 1, and in this theorem 1 we solve example of simply supported beam. Okay, this is our third example. Now before starting the example, again read the given data properly. Simply supported beam of span 6 meter is carrying a point load of 60 kilonewton at 2 meter from left side. Okay, here point load is given 60 kilonewton, but from left hand side 2 meter. Find deflection under the point load, and beam is also subjected UDL 20 kilonewton per meter. Value of E is given 200 gigapascal and I is equal to given 2 into 10 raised to 8 mm raised to 4. Using Castiglione method, we find out deflection under the point load. Okay, here figure is not given, so first of all we draw the figure. Okay, simply supported beam is given, that means first of all mention here this is our hinge support. Okay, and this one is our roller support. Here mention that beam is subjected to UDL on entire span, so first of all apply UDL. Okay, here given load UDL on entire span, so first of all apply UDL, and this UDL is 20 kilonewton per meter. Okay, this point is supposed we given A, here we given B. Now from left hand side, that means here left hand side at a distance of 2 meter. Okay, distance of 2 meter, our point load is given, that is 60 kilonewton, and total span is given 6 meter. Okay, total span is given 6 meter. So here total span is 6 meter, 2 meter here, that means remaining distance is equal to 4 meter. Now here we first step find out deflection. So 60 kilonewton load, the point where we find out deflection, the load is considered as a P. Clear? Now we find out support reaction, because here simply supported beam is given. So mention here taking moment about A, because support reaction is find out with respect to any point. Here we consider A point, taking moment about A. Okay, and suppose I assume that my B reaction is in up direction. Compare anti-clockwise moment with clockwise moment. RB into distance 6 meter, so mention here RB into 6. Then this 60 kilonewton load is we assume as a P, and this rotate clockwise 2P. Okay, mention here 2P plus UDL is given on entire span 20, 6 and 6 by 2. Here mention 20 into 6 and 6 by 2. Okay, now after simplification, RB is equal to 60 plus 1/3 of P. Okay, now we find out RA. Mention here RA is equal to total vertical load minus support reaction RB. Now what is my total vertical load? First of all P. Okay, P plus second is our UDL. UDL is equal to 20 load into distance, and RB is equal to 60 plus 1/3 of P. And after simplification, my RA is equal to 60 plus 2/3 of P. Clear? This is our first support reaction RA, 60 plus 2/3 of P, and this is our second reaction RB. Okay, RB 60 plus 1/3 of P. Now we make a equation of moments. So first of all we make our table, write down segment. First value is our segment, second value is equal to our origin point. Okay, origin, then limit. After that we make a equation of moment, and last differentiate this equation of moment with respect to load, because we find out deflection. Now first segment is equal to AC. Okay, and our second segment is equal to BC. We take a segment from last point because to simplicity of limit. Now origin point is AC is equal to A and BC is equal to B. Limit is equal to 0 to 2, right here 0 to 2, and second limit is equal to 0 to 4. Now first of all consider this as a X. Support reactions rotate clockwise, left hand side clockwise plus, and this UDL rotate anti-clockwise minus. Right here 60 plus 2/3 of P into X, and this UDL rotate right here 20 X and X by 2. Now del mx by del P, this means this term is 0. Okay, and here 60x is also 0. Remaining term is this 2/3 into P and P. So del mx by del P is equal to 2/3 into X. Clear? This is the differentiation. Now next second segment. Okay, now consider this as a X. This support reaction rotate anti-clockwise, right hand side anti-clockwise positive. So mention here RB is equal to 60 plus 1/3 of P into X, and this moment rotate clockwise, and negative moment minus 20 into X and X by 2. Here again del mx by del P, this term is 0, 60x is also 0, remaining term is equal to 1/3 into X. Now clear? Now we find out our deflection. Okay, for that again put the value in equation. This is our simply supported beam. Complete this, and UDL load is applied. Okay, this UDL load is equal to 20 kilonewton per meter. From left hand side point load is given 60. Okay, this is our 2 meter distance, and this one is our 4 meter distance, A, C, and this point is B point, and 16 kilonewton is considered as a P. Now what is the equation of deflection? Deflection is equal to 1 by EI, limit of 0 to L, then mx and del mx by del P into dx. Clear? Now one by one we put the values. Deflection means del. First segment, our AC segment, 1 by EI, limit is given 0 to 2, and multiply our first term, that is 60 plus 2/3 of P into X minus 20 X square by 2. Okay, this is my first segment, and multiply with our del mx by del P, that is 2/3 into X. Okay, and dx. Now second, 1 by EI, limit is equal to 0 to 4, and second term is 60 plus 1/3 of P, then X minus this 20 by 2, we write here 10x square also. Okay, 10x square, and multiply with 1/3 into X into dx. Now one by one we simplify it. First of all, 1 by EI, then limit of 0 to 2, and here first we multiply this term. Okay, after multiplication 40x square, 1 by 1. Okay, here I am write down 40x square, then 4 by 9 px square minus 20 by 3 x cube. Okay, and dx, plus our second term 1 by EI. Okay, limit of 0 to 4 in bracket 20 x square plus 1 by 9 px square minus 10 by 3 x cube and dx. Now one by one integration, we must simplify this term. Okay, first and second, first and second. Now one by one integrate this term. 1 by EI. Okay, first is integration x square, x cube by 3 plus 4 by 9 as it is. P, integration of x square is equal to x cube by 3 minus 20 by 3 integration of x cube, x raised to 4 by 4, and limit is equal to 0 to 2, plus second 1 by EI. Okay, and here integration 20, then x cube by 3 plus 1 by 9 p integration x cube by 3, then 10 by 3 and integration x raised to 4 by 4. Okay, limit 0 to 4. Now here we put our simplification is equal to 1 by ei. Okay, first is equal to 1, put p is equal to 60, right here put p is equal to 60, and after multiplication answer is equal to 151.11 and second term is equal to 355.55 by ei. Okay, put x is equal to 2 and p is equal to 60. Now my answer is equal to 506.66 divided by ei, and here we find out deflection. The unit is kilonewton into meter cube. Okay, 506.66, 1 kilonewton is equal to 10 raised to 3 and meter cube is equal to 10 raised to 9, divide by e. E is equal to 2 into 10 raised to 5 and I is equal to 2 into 10 raised to 8. Now deflection at C, that means del C, we find out 12.67 mm, and this answer is positive, so indicate in down direction. Okay, here we find out deflection of simply supported beam with Cassie-Coulomb theorem 1. Okay, now we derive our next theory, and this theory is for strain energy due to axial loading. Okay, now first of all, strain energy due to axial loading, we prove the equation of axial loading that is related to strain energy. For that we consider here bar, and this length of this bar is equal to L and cross section area is equal to A. Because of this axial loading, which is act as a gradually, and our bar is deformed and this deformation is delta. Okay, ultimate our target is to find out the equation of strain energy due to axial loading for Cassie-Coulomb theorem 1. Okay, now what is strain energy? Strain energy is equal to work done, and work done is equal to average force into deformation. Okay, look at this. What is work done? Work done is equal to average force that is act on body, and because of this our body is deformed and deformation. Okay, now if we take force as a average, then we have to take 1/2. Okay, 1/2 into p, and our deformation we take delta. Delta we can take also, or del we can take also. Okay, now 1/2 into p. What is delta? Okay, delta is equal to PL by AE. Okay, this is the equation of PL by AE. Okay, we already learned in stress and strain in Moss. Now strain energy U is equal to P into P square L to AE. This is for strain energy stored in a bar length L and cross section area A. Now if we find out strain energy due to axial loading in small element. Okay, next, if length of bar is equal to dx and area of this bar is equal to ax, that means this is for a small element, small section. In that condition, strain energy stored in a small element du, d means small element, du is equal to p square L, we consider dx because here we consider a small part, and 2ax, ax means area of small element. Okay, and E is equal to our Young's modulus. Next, if total strain energy stored in a bar, we want to find out this equation. Simply we take a limit. Okay, if we want to find out strain energy of total bar due to axial loading for Cassie-Coulomb theorem 1, then strain energy U is equal to limit of 0 to L p square dx to axe. That means simply here we add limit 0 to L. Okay, this is our final equation for strain energy due to axial loading. Now next, we derive strain energy due to bending. Okay, if our given bar is subjective to bending, what is the equation of strain energy? Again here we assume that straight bar we take and length of this bar is equal to L, and here bar is bent and this bending is due to bending moment M. Okay, and length of this small element is equal to dx. then di. Here the new term is that is di, and this di is equal to change in slope due to applied moment m. Okay, this we already study. If load is applied in Cauchy-Coulomb theorem 1, when load is applied, deflection is occur, and when moment is applied, slope is occur. Simply di is the change in slope due to applied moment m. Okay, now if our gradual moment m is applied, strain energy stored in small element, here we find out. Okay, so that du is equal to average moment. In case of axial loading, we have to take average load. Because of load, reflection is occur. Here because of moment, slope is occur. So average moment into change in slope. Okay, average moment, that means again we have to take 1/2 into m, and di is equal to here our change in slope. Okay, and here I write down di is equal to m by ei into dx. Okay, how these values come? Di, if I d with respect to dx, what is di? Di is equal to I is equal to change in slope. Here we write down d by dx. I is equal to change in slope, that means dy by dx. So finally here we write down d square by dx square. And if you remember what is d square by dx square, that is equal to m by I. So here I write down di by dx is equal to m by I. That means di is equal to m by ei into dx. Clear? Okay, so here I put the value of this di is equal to m by ei dx. Okay, now next. Okay, now du is equal to m square 2a into dx, m into m square, then dx n in denominator 2ei. Next, if we want to find out this equation for entire bar, then here we take strain energy u is equal to limit of 0 to L m square 2ei into dx. Okay, that is this equation is simply for find out strain energy due to bending for entire span. Now we solve one example of axial loading. Okay, for that again we refer our given data. Okay, in this example, find out deflection at C as shown in figure using Cauchy-Coulomb theorem 1, where E is equal to 2 into 10 raised to 4. In first area is given 80 and second area is given 120. So right here first of all A1 is equal to 80, then A2 is equal to 120 mm square. Okay, because millimeter is given, mm square, and second L1, first length of bar is equal to 80 mm and second length of bar L2 is equal to 70 mm. Okay, in this two bar, first and second area is different, but common thing is that our actual load here P is equal to 400 Newton is given, and that is our actual load. Horizontal load is represented as actual load. So right here P is equal to 400 Newton, and value of this Young's modulus is given. E is equal to 2 into 10 raised to 4 Newton per mm square. Now what is the equation of deflection? If you remember our first statement of Cauchy-Coulomb theorem 1, deflection is equal to partial derivative of strain energy with respect to load, that means del u by del p. Okay, here we write down capital del u divided by del p. Now what is u? U is equal to summation of strain energy of part 1 and strain energy of part 2. Now here strain energy due to axial loading we use because horizontal load is given. What is the equation of strain energy due to axial loading? Just we derive, that is P square L 2AE, because here we find out total bar but length of bar are different and cross section area is different. So here we can't take limit of 0 to L. Here we add strain energy of two different part. Okay, now one by one, common thing is our load, then area is different, sorry, length, okay, and Young's modulus. So common values p square, second is 2, and here e. Okay, now L, first we given L1, then divide by A1, second L2 divide by A2. Okay, now one by one, p square divide by 2 into Young's modulus. ठीक है, then L1 is given 80, then A1 is given 80 plus in second L2 is given 70, and here A2 is given 120. Okay, now after simplification we get right here our strain energy U, energy U is equal to p square 2e common, and simplification of this term 1 plus 0.583. Okay, that is equal to p square, then 2e and 1.583, that is u. Now deflection is equal to, if you remember, deflection is equal to del u by del p. Okay, so simply del, and our answer of this u is equal to p square by 2e into 1.583 and del p. Okay, differentiate with respect to load. So here we write down 2p into 1.583. Okay, next divide by 2 into e. Now one by one put the value. Deflection del. Okay, p is given 400 Newton, 1.583, then 2 into Young's modulus is equal to 2 into 10 raised to 4, and after simplification my answer is equal to 0.03166 mm, and this answer is positive, so here we indicate sign right hand side, and deflection we find out at C point. So our final answer del C due to axial loading is equal to 0.03166 mm. Okay, in right direction. Okay, here our chapter of slope and deflection is complete. In next section we start with our new chapter. Okay, just now we stop here. Okay.